The universe. It consists of galaxy clusters. These clusters are made up of separate galaxies. Each galaxy consists of planets, stars, and black holes. They are enormous, boundless structures, objects of unimaginable size. Let's narrow our focus even further. You, me, him, everything we see. Humanity, tiny life forms roaming on a relatively small planet, orbiting a star in a galaxy within a galaxy cluster. Everything we humans have created, everything we see around us, everything we can touch, everything I just mentioned, and everything I don't have time to mention. It is made up of atoms, a tiny piece. It lies at the foundation of the entire universe. The atom, the building block of everything. Now, we started with Newton, even earlier than that, and we got to Einstein. We talked about classical physics. Einstein corrected Newton's shortcomings, and at some point we thought we understood the universe. Everything was beautiful. We thought we understood how galaxies, stars, all celestial bodies, and everything on Earth moved, and what rules governed them. Humanity had come up with a kind of theory of everything, but we couldn't have been more wrong. In fact, we understood very, very little and could explain very, very little. The reason we thought this was precisely because of the building blocks of everything I just mentioned. Atoms, because in the world of this entity we call the atom, all the rules we had painstakingly built up over centuries had been shattered. All the formulas, all the equations we thought explained everything had lost all their validity. Everything we knew, it was a lie. Space now had a new master. A new law that would make classical physics look like child's play. Quantum physics, also known as quantum mechanics. As I said, the set of rules that governs the universe of atoms, the subatomic microscopic particles that make up all stars and all matter. And these are rules that we cannot possibly understand without entering this world, without stepping into this universe. A universe pregnant with truths and events that would most likely drive us mad if we witnessed them with our own eyes in our daily lives. That's why, before we get into the subject, I ask you to forget everything. But I'm going to ask you to forget everything you know, all the physics you've learned up to this point, everything I've explained in my previous videos. Forget it. First, let's make this clear. Beyond all this craziness, beyond all this unpredictability, quantum physics is indisputably the most successful and groundbreaking development in the history of science. By the end of this series, you will understand why much better. So, how do we know that these laws, which seem so incredible, so extraordinary, and which entered our lives only 100 years ago, are real? Because quantum mechanics has been tested more than any other law and has passed every single test without exception. And we must also remember this. As much as we love classical physics, as much as we admire Newton and Einstein, quantum physics essentially describes the universe of atoms. And since atoms and subatomic particles are the basis of everything we know, quantum physics actually offers us the true reality, the explanation for everything. And perhaps it is quantum that gives us the explanation that brings us closest to the answer to the question, why are we here? So how did we discover quantum physics? Its story is just as interesting. It all started with light again, with the phenomenon we know as black body radiation. Don't let the name scare you. Simply put, we are talking about absolute zero. You may have heard of it. The lowest temperature a substance can reach in nature is negative 273.15 degrees Celsius. And no substance can have this temperature because it means that the energy of a substance is also zero. Scientists are still working on it, but when you cool a substance to this level, very strange things happen. Everything above this temperature, everything in the universe has a temperature, and everything that has a temperature has energy, and everything that has energy, but everything is also a source of light. It emits light. Do we emit light too? Yes, we just can't see it because it's outside the visible spectrum. Because with our heat and energy levels, we emit infrared light. It's not impossible to observe though. You can easily see the light emitted by humans with any thermal camera. You are a source of light. I want you to think about that for a minute. Isn't that beautiful? Anyway, so we said everything emits light, but everything emits different light. When heated, every substance emits light at different temperatures, different wavelengths, visible or invisible, ranging from X-rays to gamma rays. For example, when you heat some metals, we see a color that changes from red to yellow, then to white, and then to blue. We even measure the temperature of some celestial bodies this way. For example, a neutron star is always depicted as blue. This is because its surface temperature is extremely high. That's the question. Why? Every substance emitted light in different colors at different temperatures. It seemed like a very simple question, but it wasn't. Many scientists worked on this for a very long time, but no answer could be found. The most obvious evidence of this would appear after the invention of the light bulb, a situation scientists could never have predicted. Glass prisms are involved again. If you remember the video about colors, Newton discovered how colors are formed thanks to a glass prism. After the invention of the light bulb, scientists were experimenting with different materials in hopes of finding more efficient bulbs. When they heated different gases, they noticed something very strange. When they looked at the flame produced by heating the gases through a prism, they saw that the colors appeared as distinct lines, separated from each other, as if drawn with a pen. Under normal conditions, colors should appear continuous, like a rainbow. But how had this happened? No one, absolutely no one could come up with a proper answer or formula to this problem, except for one person, a man who was seriously obsessed with this question and thermal radiation, a man who, despite failing dozens of times, never gave up, working for years on a single question, devoting himself to finding the answer to that one question day and night to make one of the most important discoveries in the history of science, and the man whose discovery would completely change the world, Max Planck. Like I said, the man was obsessed. He had tried every possible approach. He had used every formula to explain the situation, until he added a constant to the equation, until he added the constant we call Planck's constant. The year was 1900. As soon as he added this constant, all the pieces suddenly fell into place with a loud bang, explaining the wavelength at which light emitted from a substance would propagate. With this formula, he said that for a substance to produce light at a certain wavelength, it had to make a sacrifice. That sacrifice was energy, and there was a certain limit to the energy that could be emitted from a substance at each wavelength. For example, a substance emitting light at a low frequency required low energy, while one emitting at a high frequency required high energy. And this constant, these limits, told us the minimum amount of energy emitted at each wavelength, and that light was not actually a wave, but a particle, that it was emitted in packets. He called these packets quanta, a word meaning number, quantity. Its plural is quantum. And this was precisely where quantum theory began. At the time, this discovery didn't mean much to even him. He had achieved something, but he wasn't very confident about the results. He even considered not publishing his discovery. At that time, neither he nor those around him nor the scientific world understood it. No one knew that Max Planck would fundamentally change the world, shake the foundations of classical physics, demolish it, and open a huge door for all of humanity. He was unaware, except for one man. Guess who? Albert Einstein, of course. Einstein would be the first to realize how important this event was. He would take this incredible discovery and develop it, publishing his work exactly 5 years later in 1905. This was the work in which he explained what we now know as the photoelectric effect. This topic, which figures like Hertz had also worked on before, had never been fully understood because until Max Planck came along, everyone thought light was a wave. After Planck discovered that light was carried in packets called photons, Einstein addressed the photoelectric effect and essentially said the following. When a light particle, or photon, with a certain energy level hits the electrons in the atoms of a metal surface, the electron is released. And because it was the photon that caused the electron to literally fly off the metal surface, he called it the photoelectric effect. By the way, to give a few examples of why the photoelectric effect is important, many sensors we use in everyday life, solar panels, and even the invention of fiber optic cables are based on this effect. And here's another interesting fact. You know that Albert Einstein won the Nobel Prize, but it wasn't for his special or general theory of relativity, as everyone thinks, but for his work explaining the photoelectric effect. And although his work was published in 1905, he received the Nobel Prize in Physics for it in 1921. Why 16 years later? It was the same problem Max Planck faced. No one understood how important this discovery was. No one could grasp how extraordinary and groundbreaking quantum physics was. Einstein's work was what gradually brought quantum physics to the forefront. However, the biggest step would be taken by another man. The man you see on the left in this photo, next to Einstein, biting his nails, Niels Bohr.
The man who won the Nobel Prize in Physics in 1922, 1 year after Einstein. According to some, the most important figure who started the quantum revolution. The work that earned him the Nobel Prize was the Bohr atomic model, which, using Max Planck's formulas and inspired by Rutherford's atomic model, produced the image that comes to mind when we say atom today. This model essentially states that the fundamental explanation for light propagating at different wavelengths, as mentioned earlier, could only be understood at the atomic level. And an atomic particle is like a solar system. Electrons move around the nucleus like satellites. And when energy, i.e. heat, is applied to the atom, these electrons and the atom become unstable. To return to a stable state, it emits or releases a photon equal to the amount of energy or heat it received, whatever you want to call it. But this unstable state revealed one of the most incomprehensible phenomena of the quantum world. It's really bizarre. Now, we compared it to the solar system. For example, we know that the moon orbits the Earth in a specific orbit. But imagine there are multiple orbits, that is, alternative orbits that the moon could orbit. Do you know what happens when energy is given to an electron orbiting around an atomic nucleus? The electron suddenly jumps to different orbits, one orbit then another, but there is no transition, that is, no movement is observed. One moment you see the electron in one orbit, the next moment you see it in another. It jumps instantly. Think of the planets orbiting the Sun, for example. Imagine Mars suddenly moving into Jupiter's orbit. Jumping. Quantum leap. You may have heard of it. This is where that term comes from. Electron jumps. This is where classical physics laid down all its weapons and surrendered. This is where it said, "Gentlemen, that's all for me. The rest is up to you." But of course, for a group of scientists led by Einstein, this was unacceptable, and it would become a battle, a great battle. Surely everyone has seen this photo, a kind of constellation of the most important geniuses in human history gathered together. Einstein, Max Planck, Niels Bohr, Heisenberg, Lorentz, Max Born, Dirac, Compton, Broglie, Schrödinger, Fowler, and Marie Curie. Almost everyone was there. An incredible atmosphere. This is also where one of the greatest battles between quantum physics and classical physics began, as recorded in history. It was the conference where Einstein drew his sword against the quantum world he had almost single-handedly initiated. And if we return to this photograph, it was after this conference that the meetings we know as the Albert Einstein and Niels Bohr debates began, lasting for days and months. Debates in which Einstein attacked quantum physics with various arguments, and Niels Bohr defended it fiercely. And regarding this quantum leap, this physics based on probabilities, Einstein wrote the following in a letter to mathematician Cornelius Lanczos. "You are the only person with whom I share my attitude towards physics, the belief in grasping reality, simply, plainly, and as a unified thing. This uncertainty principle seems like peeking at the cards in God's hand, but him rolling dice and using telepathic methods, I can't believe that for a moment. We remember this conversation as God does not play dice. These words, thought to be a comment on religion, were actually said in response to the uncertainty principle of quantum physics. Niels Bohr responded to this comment by saying, "Albert, stop telling God what to do." I think we need to pause here. We need to digest all of this. It can be difficult for people to accept that everything they know and believe in is being destroyed. I think this is one of the biggest problems with the education system. Especially when it comes to science, it's taught to people as a dogma. The constant suppression of critical thinking, and the notion that accept everything as it is not your place to question, is, I think, the greatest sin of academia. Even the discoverers of all these laws of physics that are now the subject of books were not so sure. That is the beauty of science. If Newton's laws had been dogmatized, if Einstein hadn't said, "Wait a minute," if Max Planck had said, "That's the way it is, I'll just accept it," if Niels Bohr hadn't said, "There's a problem here, there must be an explanation," if Schrödinger and Heisenberg hadn't engaged in a kind of war of wits, do you know what would have happened if quantum mechanics hadn't emerged? We would still be riding in horse-drawn carriages and traveling by steamboats and trains. The same thing applies to quantum physics. Everyone keeps saying, "It's too incomprehensible, don't bother thinking about it, you'll give yourself a headache." But if no one had bothered to think about it, as I said, we would still be living in the Middle Ages. You'll understand why in the rest of the series. But my only request to you is this. The lesson to be learned from all this is never stop thinking, questioning, and criticizing. Only by questioning will you find the real answers. And as always, until we meet again, thank you for being here. With love.